Linear transformations to R2 and to R3. Linear transformations map each point in their domain to a point in their codomain. The linearity properties pose some heavy restrictions on the kind of transformations that are possible. We'll see in this video that the range of possible linear transformations that we can describe with a simple matrix operation is still very broad. First, we consider transformations from R2 to R2. Observe that when we know the transformation of the basis vectors in our domain, we know where everything goes in the codomain. After all, any vector can be described as a linear combination of the basis vectors. In particular, we see the entire grid move along with the images of the basis vectors. We can choose our basis vectors freely to create any linear transformation we'd like. To illustrate this, let's place something on the grid. We can choose the basis vectors such that we get some of the typical transformations: rotations, reflections, projections, shear, and scale. These are all examples of transformations from R2 to R2. But we can also go from R2 to R3. When we map the two basis vectors to R3, their images span a plane. All vectors will now be mapped to this plane. This is because they are all a linear combination of the two images of the basis vectors. Note that this is not the only transformation to map onto this plane. As long as the images of the basis vectors span this plane, it will be the range of this transformation. If we go from R3 to R2, we squash the grid of R3 to R2. Because you lose a dimension, the images of any three linearly independent vectors in R3 will be linearly dependent in R2. Indeed, the grid you see rotating is printed in 2D on your screen. To show this, we use a linear transformation from 3D space to 2D and show the image. As the grid rotates, we just keep changing this transformation. Now, let's fix this linear transformation for a while. Let's color all the points which map to the origin red. If we rotate our view of the domain, but we keep the linear transformation fixed, we see that the whole line of points is red. So in this case, there's an entire line that maps to the origin. Indeed, for any linear transformation of R3 to R2, there are infinitely many points in R3 whose images in R2 overlap with the origin. So you've seen that despite the heavy restrictions, there are many possible linear transformations.